Hey guys, we are on now 11.2, operations with radicals, and we're going to start doing adding, subtracting, multiplying, dividing. So first, let's look at adding and subtracting. In order to add and subtract radicals, they must be like radicals. What does that mean? It means they must have exactly the same thing underneath of the radical. It has to be exactly the same. Then you're just going to combine like terms. Okay, so we want to simplify these expressions by adding or subtracting. Well, let's think of an easier problem, like 2x plus 5x. We know those are like terms because they both have x, and x is to the first power. So we just add the like terms, and 2 and 5 are 7, and the x stays x. So it's going to be the same idea here. We're going to add the numbers out front, the coefficients, and the square root of 7 is just going to stay the same. So first, decide, are they like radicals? They both have square root of 7 underneath. So I would say definitely those are the same. That means they're like radicals. That means we can add them. So 3 and then 2, that gives you what? Well, wait a minute. Let's make it an easier problem just to make sure we know what we're doing. Pretend those square root of 7s were x's. We certainly know those are like terms, and we should definitely know that equals 5x. It's the exact same idea here, except for the x's are square roots. So the 3 and the 2 are 5, and square root of 7 will stay square root of 7. So you're not changing the radical. It has to remain the same. All right, number 2. Are these like radicals? No. But this is going to bring in some stuff we learned in 11.1. We have to be able to simplify the radical first. Square root of 3, you would want to know, does it have any perfect squares? Can you divide by any perfect squares? And 48, can you divide by any perfect squares? Well, that means we need to list out our list of perfect squares. And remember, that's just 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, and so on. You got to go at least through the number you have. 48 is our biggest number, so I went to 49. Is 48 divisible by 36? No. 25? No. 16? Yes. Okay, so square root of 3, square root of 48, we can turn that into square root of 16 times the square root of 3, because 16 times 3 is 48. So then we have square root of 16 becomes the 4, and square root of 3 stays square root of 3. Square root of 3 we know is not divisible by any perfect squares, so that just comes down. We bring down the minus sign, and looky there, now we have like radicals. Well, what number's in front of that square root of 3? It needs to have a coefficient, right? Well, if there's nothing written there, we must assume it is a, what do you think? It's got to be a 1, right? Because 1 times anything isn't going to change that anything. So 1 times the square root of 3 is still square root of 3. So that means we can do 1 minus 4 to get negative 3, and then just bring down the square root of 3. Voila. All right, number 3, are those all like terms? Certainly not. Are some of them like radicals? Yes, those square root of 2's. And we need a coefficient in front of that last square root of 2. So that means we're really doing minus 1 square root of 2. So 4 minus 1 gives you 3, and then the square root of 2 sticks with them. That plus radical 3 we can't just throw away. It's got to be part of your answer, so we just tack it on at the end. 2 and 3, neither of those can be combined, and they can't be simplified. So it's just like we had a problem like this. We would still combine the x's, we just would put the y on at the end. So it's the same idea, except for the variable, there's a radical, but same process. All right, let's look at number 4. These are not like radicals, which means you need to think about simplifying. And I need to add onto my list here because I don't go through 90. So let's add some numbers. Remember, we're just listing perfect squares. That is enough now. So I'm trying to figure out 90 can be divided by what? What's the first one going backwards? So it can't be divided by 64, can't be divided by 49, 36, 25, 16, but it can by 9. And 9 times 10 is 90. 40, I got to do the same idea. Start at 36 would be my first one. The first one it's divisible by is 4. So minus the square root of 4, and square root of 10, because 4 times 10 is 40. And then square root of 9 becomes a 3, square root of 10 drops down, minus square root of 4 becomes a 2, square root of 10 drops down. And look there, now we have like radicals again. So 3 minus 2 is 1, and then square root of 10. We could just write square root of 10 here and know the one's there, but it certainly doesn't hurt to put it there. All right, now we're going to multiply and divide radicals. Still kind of using that product property of radicals we learned in the last section. That just means we can split radicals up, but we can also go the other way. We can put radicals together. Notice one thing I want to point out. In that product property of radicals, square root of a b equals square root of a times square root of b. Well, look at a and b are two different things. So if we're looking at this backwards, that means you can multiply anything. A and b are not the same thing, but we are still allowed to multiply them. So this is different from adding and subtracting. Adding and subtracting, you can only multiply like radicals, you can only add and subtract like radicals, but for multiplying and dividing, you can do any of them. So over here, they both had to have square root of 7, or both had to have the same number under the radical in order to add or subtract them. But multiplication, that is not the case. You can multiply and divide any radicals. So here, all you're going to do is multiply the numbers that are not under the radical. Those are called the coefficients. 2 times negative 4 is negative 8. And then multiply the radicals. Square root of 2 times square root of 6 gives you square root of 12. But of course, you're not done yet. What else do you think you're going to have to do? Same as all our other problems, we have to simplify that radical. Okay? So again, you multiply the stuff that's not under the radical, and then you multiply the stuff that is under the radical. Very different from adding and subtracting. Okay, I'm going to use these things over here so I can just paste them. There we go. All right, so I'm trying to figure out what square root of 12, what perfect square root of 12 is divisible by. I'd start with 9, certainly not by 9, but it is by 4. So the negative 8 drops down, and we're multiplying square root of 4, square root of 3, and then we turn square root of 4 into a 2, throw that multiplication sign in there, and then square root of 3. Negative 8 times 2 is negative 16. Square root of 3 goes on at the end. Simple as that. Now this one you should recognize as distributive property. There are two things inside the parentheses, two terms. Terms are separated by plus and minuses. So 3 squared root of 2, that's all one term. So you're only going to distribute that to that one time. Sometimes students will think those are two different terms. They're not. 3 squared root of 2 is all one term. It's multiplication, one term. So 4 times 3 gives you 12. Square root of 7 times square root of 2, square root of 14. And then minus There we go, minus, and then 4 times 2 is 8. Square root of 7 times there's nothing back there, so it stays square root of 7. Now again, we need to see if we can combine them, adding and subtracting, but they're not like radicals. So, can we make them like radicals? Is 14 divisible by any perfect square? Not 9, not 4, 1 and 0 aren't going to help you. 7, not 4, 1 and 0 aren't going to help you. So that means you cannot simplify either one of these. Therefore, that is your answer. Do not try to add or subtract them. You can't. All right, quotient property. So now we're getting into division. Again, you can divide any radicals. They don't have to be like. Same as for multiplication, but different from adding and subtracting. The first thing this quotient property is telling us is that you can separate these into two separate radicals. So this becomes square root of 16 over square root of 49. Well, this is pretty nice because take a look at our list of perfect squares. Let me put it over here on this page. There we go. 16 and 49 are in the list. That means those are perfect squares, so there's not going to be any radicals left. 4 and 7. That's your answer. Nothing else to do. Okay, number 8. First, you want to try to, oops, wait a minute, before I do, oh, that's an 81. How did I do that? I need to add on because I'm going to be looking at a bigger number. So the very first thing I really need to do is I need to write these as two separate radicals. And now again, look at that. I have perfect squares. So that's just 11 and that's just 5. And we're done. Voila. All right, let's move on to some harder ones. It is not appropriate to leave a radical in the denominator of a fraction. Multiply by a form of 1 to get it out. This is called rationalizing the denominator. So if you pay attention to the answers from the last two, we had no more radicals left, particularly in the denominator. But you might have problems that do have radicals in the bottom, and you can't do that. You can't leave that as your answer. So you have to multiply by what we call a magic 1 or a creative 1. Like 4 over 4 is 1. Okay? So we could pick some fraction that is equal to 1, but that will help us out when we do this process of rationalizing the denominator. So we have 3 over square root of 11 for our first problem. Square root of 11, let me get this list one more time. There it is. Square root of 11 cannot be simplified. It can't be divided by 9 or 4, and we know 1 and 0 aren't going to help us. So we multiply by a magic or creative 1. And it's just going to be whatever the denominator's radical is. You have to do it on top over the bottom because the same thing over the same thing is equal to 1, and you can always multiply by 1 because that doesn't change a problem's value. So when we do that, we've got to do it on top and bottom. This just becomes 3 square root of 11. One's under a radical, one isn't, so you can't actually make it like 33 or anything. And then on the bottom, 11 times 11, those are under radicals, so you get 121. And look at that, that's a perfect square. That will always happen when you are doing rationalizing the denominator. You'll always end up getting rid of the radical on the bottom. So, just a reminder, if you have square root of x times square root of x, it's just x. So square root of 11 over square root of 11 just became 11. Now we did the intermediate step where we made it square root of 121 and then took the square root, but it's always going to work out that way. The other thing is students always want to cancel these 11s. You can't. One is under a radical, one is not, so you cannot cancel them. That is your answer. All right, number 10. We've got that radical in the bottom. That's a problem, so we multiply by it on top and bottom. On the top, 1 times the square root of 4 is just really square root of 4. 1 doesn't have to be written there. And on the bottom, square root of 16. And look at how nice that is. Square root of 4 is 2. Square root of 16 is 4. Perfect squares. And 2 over 4 can be reduced to 1/2. Easy peasy. But there's an even easier way. Look at the very beginning. What is the square root of 4? It's just 2, right? If you recognize that from the beginning, you don't even have to do any of those other red steps. You can go straight to your answer. Okay, so sometimes you don't even have to do the process of rationalizing the denominator. It'll just work out for you. All right, number 11, write it as two separate radicals. Square root of 8 over square root of 5. And then we've got to get rid of the radical in the bottom. Square root of 5 can't be simplified, so we make it times square root of 5 over square root of 5. You get square root of 40 over square root of 25. And then we need to simplify our radicals. Well, the easy one's on the bottom. That's 5. We know that's going to turn into a perfect square. So square root of 40, it's not divisible by any of these, but it is by 4. So square root of 4, square root of 10. Square root of 4 is 2. Square root of 10 stays the same, all over 5. Now again, you cannot reduce that 10 over 5 because 10 is under a radical, 5 is not. Okay, that is your answer. If it were the 10 that were not under the radical, then you could have done the 10 and 5, but not when one is under the radical and one when is not. Number 12, square root of 12 over 6. Well, if you're really thinking, you know 12 over 6 is 2, and then try to simplify square root of 2. You can't, so you're done. Okay, so if you don't have to do the rationalizing the denominator, don't do it. If you can simplify your fraction first, or take a perfect square first, do that. It'll make your problem easier. Okay, just a few more examples, a little bit longer, but the same ideas. Simplify the following radical expressions. We have 3 things happening, 3 different radicals now. The first thing you want to do is look for like radicals. We don't have any. We're adding and subtracting, so we would need like radicals. We don't have any, so then we're going to need to try to simplify each radical individually. Square root of 7 can't be divided by any of those perfect squares, so we leave that alone. Square root of 28, let's see, what can we divide that by? 4. 4 is the biggest perfect square. 4 times 7 is 28. And then I'm just going to ignore that last one just for a second. I just want to keep working on this middle one. But I know that first one's not going to do anything, so let me just drag that down. So this is 2 times 2 square root of 7. And then again, let me drop that down. 3 square root of 7. And then minus 4 square root of 7. Now, let me go back up. The 63, don't forget about it. We still got to deal with that. Anything it can be divided by, the biggest number, biggest perfect square is 9. So plus radical 9 times radical 7. That's 3 radical 7. Bring that all the way down. And look there, all 3 are perfect. Not perfect. They're oh my goodness, can't talk. Like radicals. So I need to combine the coefficients. So 3 minus 4 plus 3 gives me 2. I tack the radical 7 on the end, and look at how nice that is. 14. I've got a quantity squared. Now what students always want to do is distribute the square to everything. But you can't do that. If you have anything more than a monomial, you cannot do that. That's a mistake I see all the way through my college credit class this year. You have to write it out twice. Try to get that through your head. If you have an exponent on a polynomial, you have to write it out that many times. You cannot distribute it. So this is basically distributive property. Not distributive property of the exponent, but distributive property of the terms. 2 terms in each one. 3 square root of 3 times 3 square root of 3 is 9 square root of 9. 3 square root of 3 times 2 square root of 2, and then negative 2 square root of 2 times 3 square root of 3, and then negative 2 square root of 2 times negative 2 square root of 2. Hopefully you got all that. Middle terms, the 2 middle terms are like terms, so I'm going to combine those. Those don't cancel. They're both negative 6's, which becomes negative 12. And I just brought my first term and my last term down. Now I'm going to simplify. Square root of 9, we know is a perfect square. It's 3. Square root of 6 cannot be divided by any perfect squares, and square root of 4 becomes a 2. So we have 27 minus 12 square root of 6 plus 8. 27 and 8, of course, are like terms, and that gives you 35, and then your minus 12 square root of 6 just comes down. All right, now I want you to pause the video and do these last two yourself. Pause the video now and go ahead and do that. Make sure you do them. Don't keep watching this video until you've got it done. Okay, there's my work. There's my 2 answers. Check your work against mine. Make sure you are good to go. And good luck on your mastery check. We're almost done, guys. We're almost through the end of the year.